Hello, welcome to STEM Q&A, and today we'll be going over a problem in vector calculus integration, and this problem says let S be the portion of the cone x squared plus y squared equals z squared with z greater than or equal to 0, that is inside the sphere x squared plus y squared plus z minus 1 squared equal to 1, and we're evaluating a surface integral. So first, before anything, we need to understand what we're integrating. So it says the portion of the cone. So this is the equation of a cone right here. That is inside the sphere. X squared plus y squared equals plus z minus 1 squared equals to 1. So this is a unit sphere, but it's just shifted upwards on the z-axis. So if we were to graph this, it would look something like this. Like, as you can see, the bottom of the sphere is at z equals to 1, and then the center of the sphere is at z equal to 1. So if we were to put a cone in there, the cone and the sphere would meet at z equals to 1. And if you can see this right here, if we were to cut off where the cone and the sphere meet, it would be cut off at a plane that is equal to z equals to 1. So at the tip, where the bottom of the spheres and the tip of the cone meets, as z equals to 0. So this is what we'll be integrating, the surface integral. So the formula that they give us, they want us to solve a surface integral, ds. So we need to convert this to a double integral with a different parameterization that can be used to integrate this cone. Because we can use like simple parameterization, but like x, y, and z, but it'll be a little more difficult. For this case, since the cone, we can use cylindrical coordinates, so it will be a function of f and r and theta, and we'll see right now why I choose those. And in here, there's going to be a Jacobian. I forgot to write it in here. But this form of Jacobian is a cross product between tangent vectors. So we got tangent vector r, cross product with tangent vector theta. And you'll see why I use these two parameters. Remember, since it's a double integral, I need two parameters. Even though cylindrical coordinates gives you three parameters, you just need two. But I'll show you how you can get two. So the cross product between tangent vector r and tangent vector theta, and finding the norm. The norm just means that you square everything, you add it, and you square root it. So I'll show you guys what I mean right now. So the formula we're trying to solve would be something like this: r theta times the norm of the cross product between tangent vectors dr d theta. So this is the formula that we're trying to meet. So this right here is just 1. Like, as you can see, there's no function here. It's just ds. So there's like an imaginary 1 right here. So this 1 is just f of r and theta. That will be like the function. That will be like the surface you're integrating over. So now we're basically just solving for this right here. So let's start. So our parameters would be x equals r cosine theta, y equals r sine theta, and z equals to r. I know in cylindrical coordinates that z equals to z, but when you have the equation of a cone, let's see, you actually have r squared right here. Z is just equal to r. As z increases, the radius increases as well. So that's why we could just make this assumption that z is equal to r, because it fits in this equation of a cone. So if we continue, have our two parameters, r and z. So we need to find tangent vector r now. So we need to find the vector in the x component, y component, and z component. So if we solve for those, so partial x respect to r, that's just cosine theta. Partial y respect to r, that's just sine theta. And then partial z respect to r, that's just 1. And now let's find tangent vector theta. So partial x respect to theta, that's negative r sine theta. And then partial y respect to theta, that's just r cosine theta. And then partial z respect to theta, that's just 0. So now to find the cross product, you need to find the determinant. So tangent vector r times tangent vector theta is just equal to I, J, K, and now we need to fill in the rest. So we're gonna fill this row with tangent vector r. So cosine theta, sine theta, 1, and then negative r sine theta, r cosine theta, and then 0. So this row is tangent vector theta. So the reason I want to find this cross product because these two vectors are perpendicular to each other. So it'll look like something like this. But if we take the cross product, you'll have a normal vector that is perpendicular to all these. So they're all perpendicular to, these are all right angles. So we need to find the normal vector. And after we find that normal vector, we find the norm of that normal vector. That just means we're finding the magnitude of it. And after that, we just integrate. So now we solve this determinant. So this is a determinant. So now we choose a row for our vectors. So it's just equals to I. And then the cross product now be the determinant of this small thing right here, of this portion. Remember, we eliminate a row and a column, and we're left with this. So plug this in right here. I'm hoping that if you're watching this video, you're already somewhat familiar with taking determinants. This is more like the differential part of multivariable calculus. So hopefully many of you viewers will already know how to take a determinant. So now we're doing in the j direction. So eliminate this row, this column. You're left with cosine theta, r negative r sine theta, and then this 1 and 0. So we'll just fill that in. And now the last, I'm pretty sure, you know, I'm talking about eliminate this row, this column, and we're left with these 4 functions there. So cosine theta, sine theta, negative r sine theta, r cosine theta. And then we just finish this determinant. So remember, take a determinant 2 by 2, multiply across, and then minus this product. So multiply this, and then minus this product over there. So now it'll be just I. Sine theta times 0 is 0, minus negative r cosine theta. So it'll be the I vector minus the j vector. The determinant of this 2 by 2, cosine theta minus times 0 minus negative r sine theta times 1. So that's just r sine theta. And then plus the last vector, determinant of this. So this is r cosine squared theta plus r sine squared theta. So if you know your trigonometry, when you see a cosine squared theta plus sine squared theta equals to 1. So if we were to factor out an r, we would just be left with this, and these two added together is just 1. So this right here is just r. So now after we have tr cross product with t theta, which is the tangent vectors, I have I just put it in this notation. It means the same thing. Theta r sine theta, and then r. So now we're gonna take the norm and think of this as like a Pythagorean theorem. You know, when you want to find the magnitude of a vector, you know, you do a Pythagorean theorem. Like if you want to find, let's say you have a triangle and you're trying to find a certain vector or a certain line, like the magnitude of this line right here, you use like your x and y component, you know, to solve like the magnitude of this line right here. So that's what we're gonna do. So negative r cosine theta squared plus negative r sine theta squared plus r squared square root. So keep going. This is r cosine squared theta plus r squared. Oh, I forgot the r squared. theta plus r squared. And once again, we see this trig identity, cosine squared theta plus sine squared theta. We factor out an r squared. That would just be equal to 1. So the cosine squared theta plus sine squared theta is 1. So we just have the r squared. And then we still have this r squared over here. And then this right here is 2r squared in the square root. We keep going. That's r times the square root of 2. So this right here is what I was solving for. And now we just fill in the missing pieces or our formula. So this was just 1. The function of r and theta was just 1, evaluating over 1. And then we found this portion, this cross product, and the norm of it, this normal vector, is just equal to this right here. Alright, and then we want to know our domains of r and theta. And as we can see from the cone, I'll bring it over here. This cone right here, the center is 0, and it only goes out to 1. Okay, so r, its domain is from 0 to 1. Theta is domain. Remember, the top of the cone, it does a full circle, so that's from 0 to 2 pi. We fill in the domains. So we got now square root of 2 times r dr d theta. And now this is just a really simple integral to solve. So remember, we want to solve the innermost integral. So that's just r squared over 2 times square root of 2. And this is from 0 to 1. Remember, this is just like single variable techniques. So we plug that in, it would just be square root of 2 over 2. We integrate that. Now we're integrating d theta. And this right here is just square root of 2 over 2 theta from 0 to 2 pi. And this right here is going to be equal to square root of 2 times pi. And that is the answer to this integral. So that is the answer to that. So thank you for watching. Please like and subscribe. Please feel free to leave any questions in the comment section below. And thank you for your time.